Hello, welcome to The Naked Scientist with Chris Smith and with Ben Valsler.
Hello, in the programme this week, a sponge that soaks up oil spills, evidence that dung beetles navigate by following the stars, how mankind came by his best friend, and why in the future you might be storing your computer files in a DNA format.
Plus, we're looking at the world of transparent electronics this week, with the scientists making materials that can beam maps of the road ahead directly onto your retina, or even allow you to browse the internet through a contact lens. But how does it all work?
If you would like to get in touch with us here at The Naked Scientists, then email Chris at thenakedscientists.com, tweet at Naked Scientists, or find us on Facebook.
The Naked Scientists podcast is powered by ukfast.co.uk.
Joining us this week for a look at the science news is Laura Howes from the Royal Society of Chemistry's Chemistry World magazine. Also, Cambridge-based science journalist Mark Peplow and Laurie Winklis, who's at the National Physical Laboratory. So hello to all of you.
Hello.
Hello. So Laura, kick off if you would and tell us about this new way to soak up oil.
We're looking at soaking up oil spills with a sponge which looks a bit like a marshmallow. It's really light and it's got lots and lots of space, just like a sponge, but it's very specific for oil. So rather than with your washing up sponge where you'd sort of soak up lots of water and oil at the same time, you can whack this onto the oil layer on top of the water and it will float and it will soak up the oil, but it won't soak up any of the water.
Wow, how's it work?
It's based on some very basic polymers that have been made into what we call a hydrophobic material. So just like you have oil and water and you know they don't mix, oil is hydrophobic and so is the sponge. It's pretty neat, and it was actually first reported in 2011 when the team who were trying to make it at Kyoto University were actually trying to make transparent what you call aerogels. So these are like gels, but instead of water, they've got air in the pores, and that makes it very light. But they didn't make something transparent, they made something white, and it looks like a marshmallow.
Who's done this? Since you say Kyoto University, they're presumably Japanese.
They are, so it's Kazuki Nakanishi from Kyoto University and his team, and they work on making these things called zero gels and aerogels.
We'll hear more about jelly in a second from Mark Peplow, who's also here. Got something that will fill an Olympic-sized swimming pool with the stuff. But how would you see this being used then? Is it simple to make huge amounts of this so if there were another Gulf of Mexico disaster, you could literally put this on the surface of the sea and soak up enormous amounts of oil selectively?
Yeah, at the moment they're only making small amounts, so you probably won't be able to do the Gulf of Mexico disaster, or if you will, it will take a long time. One of the benefits of this versus other technologies is that you can wring it out like a sponge and then use it again, so it's very reusable.
But very big hands if it was an oil slick then, wouldn't you? So more kitchen than Gulf of Mexico.
More kitchen perhaps, but I mean, obviously now that you've got this material, you can start looking at trying to scale it up. And also, if you think about it, there are lots of other applications where you might need to separate oil from water, even just down the petrol station where you might need to do that, or through industrial spills.
Petrol's getting expensive these days, isn't it?
It is. You can
get the extra drops off the forecourt, squeeze them into the tank.
And also in chemistry, we often work with different phases. So materials might be in an oil-based or a hydrophobic phase, or it might be in a water phase. And in this way, you can separate it out without the laborious washing something and separating it and washing it and separating that I remember doing in the lab.
Well, that sounds really interesting. I'd imagine as well it'd be really useful for cleaning up all of the oil that's blocking up our sewers, which is becoming a big problem. And speaking of sewage and waste and so on, I've now got a beautiful story about dung beetles.
Unlike the link, which was extremely tenuous.
Very, very, very tortured, that one. Dung beetles are remarkable creatures. Not only does their way of life rely on food from somebody else's waste, but recent research has also shown that their dung balls help to keep their feet cool on the hot desert sands. And now, recent research published in the journal Current Biology shows that dung beetles actually navigate by the light of the Milky Way. And this means that they've become the first insects known to use the night sky in this way to orient themselves.
How on earth did someone find that?
Well, it's been spotted that basically when dung beetles pick up their ball of poo, they roll it into a ball, and then they have evolved to walk in a straight line away from that dung pile. And that's because there are lots of other dung beetles around that might steal their balls. But it's been seen that on really cloudy nights, these paths aren't straight. So they're obviously doing something to orient themselves to navigate that relies on getting a clear view of the sky. So it was a group at Lund University and also the University of Pretoria in South Africa who have inspired this work. This was Marie Dacke and her colleagues. And what they did was a series of experiments, including one where they manufactured tiny cardboard caps, which they used much like blinders on racehorses, just to stop the dung beetles from being able to look up and see the stars. They then put a big curtain around them, so they obviously couldn't use the things that are sort of on the horizon to navigate. And then, and this I think is beautiful, they took their volunteer dung beetles to Johannesburg Planetarium so that they could control the night sky itself to try and work out what it was about the night sky that they used. And they found by switching things off selectively that it's not the stars necessarily, but actually that diffuse glow of the Milky Way that these insects are using. And that's the first evidence of any animal using that, and certainly the first evidence of insect.
What about when it's cloudy?
Well, when it's cloudy, they do struggle, and they obviously have to rely on other senses, but their paths are not as straight. It does take them longer to get around on cloudy nights.
I've got nothing to say. It's very hard to follow that, isn't it? I'm glad it's not me, Mark.
So I have got another amazing polymer for you. I want you to imagine that you're standing in front of an Olympic-sized swimming pool, and in one hand you've got a kilo of this new polymer. You throw it in, and within minutes the whole thing has turned to jelly. This is a polymer that basically, when it comes to forming gels, it's probably the best in the world. It's an order of magnitude better than anything else. But it's not just about making these sort of record-breaking dessert portions. It's actually the first synthetic polymer that can match the rigidity that's found in many biological polymers, and that's actually the secret to its success.
Well, since you mention it, what is it made of? Could you eat it? I mean, what's the composition of this jelly?
You probably could eat it, actually, without causing much harm. It has this backbone that twists into a helix. And from the sides of it, you have these thousands of short peptides. These are small biological molecules jutting out from the sides. Each of those have got long, floppy tails made of repeating units of ethylene glycol. That's an antifreeze that you find in your car windscreen wash. Now, what happens is that this makes it dissolve very easily in water because those floppy chains grab onto water. But when you heat it up, these tails squeeze the water molecules away, and neighbouring strands of polymer assemble into bundles about 10 billionths of a metre wide. Now, that's what makes the whole structure stiffen up, and it's exactly the same way that it works with biopolymers in a cell, say collagen or something like that. And it's exactly the same as how it works in a rope as well. You have twisty bundles, and that's what makes it stiff. That's why it's so good at making these jellies with just trace amounts of the polymer.
What could you do with it? Because you keep mentioning the biological relevance. Is that the idea of the people who've come up with this said this would make a really great cartilage for joints or some kind of subcutaneous tissue replacement or something?
You're absolutely right, Chris. Alan Rowan, who led the team at Nijmegen University, who did this, wants to exploit some of the other surprising properties of this. Unlike most jellies, when you make jelly at home, for example, you have to cool it down in the fridge to make it set. This works the other way around. It sets when you warm it up. So what they're actually investigating now is whether you can take a solution of this polymer from the fridge, it's nice and cold, pour it on a wound, and the body temperature makes it turn into a gel. When you want to take that off again, when the wound is healed, you just apply an ice pack and it comes off. They're actually trying this out now. Rowan told me that they're currently doing experiments on a leg of pork that they've had in the oven at 40 degrees, and they're slapping this stuff on and seeing if it actually works.
Have they done the swimming pool experiment?
They haven't, no. When I talked to Alan about this, he was so excited. He was using this as an example to illustrate just what a good gelato was. I do think, I have a sneaking suspicion he really does want to try it out.
And if you did it, you'd be really unpopular with the cleaner, wouldn't you?
It would take a long time.
So is the idea that they'll be able to add active groups to it? So is it so reliant on its structure that actually we'll struggle to put those antibodies bacterial compounds or the growth hormones that you'd want to use an artificial biological structure.
This is interesting, actually. This is one of the things that they're already doing. That's unpublished as of yet, but they are trying to add these different biological functional groups off the side of the polymer. One of the interesting things, actually, these ethylene glycol groups, these flappy side chains, that makes the material actually invisible to the body's immune system. There are various drugs, protein drugs, which are called pegylated drugs. PEG is polyethylene glycol, and that makes them sneak in under the immune system's radar. So they have tested this particular new polymer out, and it is completely invisible to the body's immune system.
Thank you, Mark. Laurie, it says here Laurie's on the rebound. You're not. You're going to talk about the rebound effect, though, aren't you?
Yes, indeed. We're all aware of the kind of energy question, and everyone's trying to do their bit to be a bit green. And a lot of that includes things like energy-efficient light bulbs, for example. But there's a lot of economists who believe in this paradox called the rebound effect, which basically states that if you improve the efficiency of something, instead of encouraging people to use it better, you actually encourage people to use it more. So you might improve the efficiency, but if more people are using it, does that therefore cancel out the benefit?
Indeed. So I make my car 15% more efficient and it costs me 15% less, so I drive 15% further, cost to the planet net neutral.
Yes, exactly. That's the argument that comes from the economists. But there's a group of environmental scientists who are based at Yale who see this argument about this paradox, about this rebound effect. They kind of see it as a distraction to the energy efficiency question, in that they believe that economists are overstating its importance, and that what they're doing is basically adding lots of numbers together and getting a net result. Their argument is that often when you have one of these effects, it removes the possibility of another effect. So actually the overall impact is still lower than the number of people driving more, for example. So yes, I might drive more, but I don't drive more enough to completely cancel out the fact that my car is more efficient.
Have they got any evidence to support that, or is this just their contention?
It's a bit of both, I think, to be completely frank. There's a lot of evidence to suggest that it's actually that these effects have been overstated. So they've done a lot of work into looking at simulations of energy savings, and then looking at how economical that allows people to make those decisions economically. And what they've kind of found is that people respond more to price changes rather than efficiency changes. So yes, people are driving more, but still the overall effect seems to be that the energy efficiency it's worth trying.
So is this sort of thing considered at the moment when people are designing the lifetime efficiency of a new product? Do they already count that into their statistics, or is this something that we sort of add on afterwards?
I think basically what seems to happen is that it is considered, but because there's so little agreement on the size of this effect, so economists are saying, it's a 30% increase in driving just because you've improved the fuel efficiency by 5%, and you've got the environmental scientists saying that those numbers are overstated. Actually, the major problem is that it's agreeing on the measurement of it. So if people are kind of going into it with a little bit of colour, shall we say, so a little bit of bias. So some people are considering it and others don't seem to be.
I mean, surely the answer here is you just got to jack the price up, haven't you? So you make it more efficient, but you've got to have an escalating price, because if you do that, then people will still feel it in the pocket, but the planet doesn't suffer into the process. Yeah,
exactly. I mean, the reality is that this rebound effect, is real and it's measurable to some degree, but the only way that you're actually going to benefit in the long term is having that in parallel with a reduction in consumption. And the best way to do that is to tax people out of it, really, which sounds a bit serious, but
sounds pretty vicious.
Indeed, yeah, unfortunately it does.
You go along with that, Mark?
I mean, this is one of those occasions where you can look at the future scenarios for different types of energy-efficient products, and there's a lot of speculation about what impact it's going to have on the economy, what the take-up is going to be, what the ultimate outcome is going to be. It's only really by doing these sorts of analyses that you can actually help to make policy making, basically, in these things. And as with most energy-efficient technologies, most new environmental initiatives, there's got to be a bit of stick there that goes along that is supported by this evidence. So taxation, I'm afraid, is likely.
Death and taxes, isn't that what they say?
Inevitable, Chris.
Mark, thank you. Now, also this week, there's a paper which caught my eye. It's in Nature. And it's by researchers at Uppsala University in Sweden, Erik Axelsson and his colleagues. And they're actually asking the question, well, where did dogs come from and why? Now, we've known for some time that you can trace dogs back in the fossil record about 12,000 years or so, and maybe even to 30,000 years. There's some bones from Siberia that sort of go back that far. But the question is, what made a dog appear in the first place? And dogs are obviously very closely related to wolves, and the current theory is that humans domesticated them from wolves. Why they did that, we don't know, and how it came about, we just don't know. We just know that from about 12,000 years ago, there are dog fossils that are found in association with human remains, showing that there was a close association between the two. So they've actually taken a genetic approach to try and solve this one. And what Erik Axelsson and his colleagues did was they went and got DNA samples from 12 wolves around the world and then 60 dogs, domestic dogs. Now, the reason for using so many dogs is because dogs have been bred into a number of different breeds by humans, and so you've got to counter the effect of this selective breeding. So they've got 60 different dogs representing 14 different breeds. And owing to the power of modern molecular biology, they just genetically sequence the whole lot. And they then used single nucleotide polymorphisms, SNPs, these molecular signposts, to look for areas of the DNA that were consistently different across all the breeds between the dogs and the wolves. And what they found was 122 genes which appeared to be consistently different in the dogs compared with the wolves. And then they started asking, well, what do these genes do? A lot of them map onto the brain and the nervous system, and we know that dogs have smaller brains than wolves. They also have different behavioural traits, and that's probably the crux of it, because there's a study in silver foxes, I think, isn't there, which showed that you can selectively breed certain traits if you go through generation and generation of selective breeding. So a lot of it's down to brain and behaviour. But there was one really interesting thing that came up, which initially you think that it's a mistake, and then you realise it's actually fundamental to the whole process. Genes were coming up which relate to how these animals break down starch, because they found that the amylase gene had been duplicated 40 times in the dogs. Wolves have only one copy. Why would dogs need a 40-fold duplication of their amylase gene? Well, of course, the wolves are eating an obligatory meat-related diet, aren't they? Whereas the dogs, they're saying, the dogs were creeping up on human habitation. And 10,000 years ago is conveniently the time when people started, actually, to have agriculture. So you've got people going into villages, they've got farmers and agriculture, and that means that the kind of things people are throwing away, that these early dogs are probably scavenging on, are going to be very cereal and starch-dominated things. So therefore you're selecting from the wolf population animals that can actually get metabolic reward out of this leftover food from humans. And humans are going to chuck dogs titbits and things, aren't they? And as a result, it has strongly selected in favour of the ability not just to process starch, because they make amylase in pancreatic juice, but they also have got more receptors in their intestine for glucose, which is the breakdown product of amylase. And they're saying, and I quote from the paper, they say, our findings suggest that the development of agriculture catalysed the domestication of dogs. And they say that this week in the journal Nature.
Is there any indication as to the timeline for these things happening? Could it be that the shift in diet then led to a change in behaviour, which then led to the new adaptations, the new selections for the different brain, for example? Or could it be that perhaps having a different brain, perhaps being more likely to spend time around humans, then forced them into a situation with a different diet, which then selected a different population? Is there any way to tell?
It's a really good point, and we don't actually know what the order of these things is. We just know that the dogs are obviously going to be the product of the acquisition of various traits that meant that they were much better at getting on with humans, and they were going to be tolerated by humans and therefore serve some kind of beneficial purpose for the humans, being guard dogs, for example. And they've also got to survive on things that humans are going to chuck away, because people are not going to give a premium thing like meat, which is a premium commodity, to the dog. They're going to give it offcuts, obviously, but they're going to give it other stuff, and the dog that can eat the junk is going to do much better than the dog that can't. So I reckon that's the reason. Mark?
So does that mean then that 10,000, 12,000 years ago, there were wolves who naturally had the chance mutations that gave them a few extra amylase genes? So they had to have that to start with, to give them some little advantage in feeding on early agriculturalist scraps. And then that selection pressure increased the number of amylase genes.
Yeah, and I think that's why they've gone into this, and they've said, look, there's copy number variation, so the number of copies of the gene has amplified over time. And the fact that dogs have got that, but the wolves have stuck with one copy, says that perhaps one particular substrain of wolf happened to increase the number a bit, and that gave it the ability, like Ben says, to encroach on human settlements and get nutritional benefit from the leftovers that humans turfed out. And at the same time, you've got humans trying to exploit these animals because they're very good at warding off other predators and things like that. And so, it's a self-fulfilling prophecy in the end, I guess. You can actually pick up the references to all of these stories off our website at nakedscientist.com/news if you want to follow up on any of them. But thank you very much to Chemistry World's Laura Howes, to Laurie Winklis from the National Physical Laboratory, she's our Naked Scientist physics correspondent, and to Mark Peploe, journalist from Cambridgeshire. And this is The Naked Scientists with Chris Smith and with Ben Valsler.
Still to come, transparent electronics. This is technology that will project a map of the route onto your retina so we don't even have to take your eyes off the road. We'll talk to the people behind it very shortly.
Now, what's the most efficient way to store data? You might think that it's on a microchip or on some kind of laser disc, but the answer is actually lying inside your own cells. DNA may actually be the best option for archiving data. Dr. Nick Goldman from the European Bioinformatics Institute in Hinxton has developed a method for storing computer files in DNA format. Hello, Nick.
Hello.
So, first of all, just to sort of clarify, how does a computer store data?
So a computer, it shows you a picture or it plays you an audio file, but actually what it's storing is zeros and ones on a hard disk or in its memory, and it's also storing information about the code that's needed to convert the zeros and ones back to whatever it is.
So when we say binary, it is literally 0 or 1, and it knows the code for what a sequence of noughts and ones mean.
That's
and
right.
How that translates into something on the screen or whatever you choose to do.
That's right. And of course, there's a different code for if that's a document in a word processor or a PDF file or an MP3 or whatever.
And when you save that onto your hard disk, you're effectively putting that pattern of noughts and ones on your hard disk or a series of little pits on the surface of a CD player.
That's right. Pits on a CD disk that will go in a player or magnetisation on the platters of a hard disk drive.
So why did you decide, well, OK, we're going to do it with DNA instead?
We were inspired to do it because of the difficulties we have at the European Bioinformatics Institute, where we're responsible for storing vast amounts of biological data and serving that over the internet to the whole world of molecular biologists.
So you mean DNA sequences and things that people upload to your database?
It's not only DNA sequences, but that certainly is some of the largest amounts of information.
Well, how much information are you storing then?
We are storing and serving to the world 3 petabytes of information at the EBI at the moment.
Gosh, that is quite a lot. That's a lot of hard disks, isn't it?
It's a lot of hard disks.
And so that you said, look, this is such a huge number of hard disks. Is there another way?
That's right. We're running out of money to store all the information that's being sent to us these days. And so over the years, we've had a number of discussions about whether there were any alternatives. And we've had a number of very serious discussions about alternatives. But one evening in the pub in Hamburg, we had a rather frivolous one and noted that DNA itself, as it happens, is also a very good way of storing information.
Yeah, indeed, because, I mean, otherwise nature probably wouldn't have, over millions of years, arrived at using DNA as a good choice.
It's a bit chicken and egg how you have this discussion, but because DNA is good, so we're discussing DNA. So, yeah, that's right.
So how did you then say, well, look, can we use DNA instead of a computer hard disk?
Well, we said exactly that, and then we bought another beer and got some more napkins to write on and started working out if we could actually do it in some sense. And by the end of the evening, we'd worked out that we could do it because the technologies that are now being developed for genome science allow us to read DNA sequences. They're getting better at allowing us to write DNA sequences, which is really useful for certain particular experiments you want to do. And if you sort of stick all these technologies together, you sort of glue it together by courier services and so on, and emails to each other, then we could do the whole thing. We could start with a hard disk drive, go via actual physical DNA and back to something on a hard disk drive that hopefully would be the same as we started with.
Well, DNA's got 4 genetic letters, A, C, T and G.
Yeah.
a hard disk has noughts and ones.
Yeah.
So how did you get around that?
Well, it's very easy to do the coding at a naive level. If you take two noughts and ones next to each other, then there's 4 different ways you could get something. You could get a nought and a nought, a nought and a one. I'll go through them all for you, folks. A 1 and a nought, and a 1 and a 1. So there's 4 choices there. So you could just assign to each pair of zeros and ones one of the letters A, C, G, or T. And that might work, but we wanted to do something that was a little cleverer. But in particular, we were thinking in the longer term, if this was ever really going to be useful, we'd want to add in some real life stuff like error correction into the codes. And that meant we had to sacrifice a bit of the efficiency of coding, but we can build in various techniques in the code that will mean if we eventually are reading back a bit down the line here, we read back some of the DNA. If something has gone a little bit wrong, maybe we can recover from that error and not lose any of the original information.
So you take the sequence of noughts and ones that the computer's got, you then translate that into a sequence of DNA where the genetic letters mean either a naught or a 1 or a 1 or a naught or the combinations you said. You then make artificially the DNA sequence.
There's one little part in the story there you skipped over. Humans can't yet make very long strings of DNA. We can make fairly short ones, up to say, well, nowadays up to about 200 nucleotides, 200 letters long. So we knew we'd need some system that would take the very long message that's in one computer file and break it into little pieces. So still in the computer, we wrote a series of letters A, C, G, and T, and then we cut it up into pieces of 100 letters each. And then we added some more information to each one of those little segments that would tell us where it came from, which file it belonged to.
The address, if you like.
Exactly, indexing and where in that file it belongs. So we end up with these slightly larger designs, you might call them, about 120 letters of DNA. And then we wrote that onto a computer file. We sent it over the internet to our collaborators in California. And they're the people that have the technology that actually makes this stuff. And they can make pieces that length.
And you translated a whole load of data into DNA.
Yep.
And then how do you get the DNA data back out again?
So they put it through their machine in California, which is sort of it's actually like a kind of inkjet printer or an equivalent of an inkjet printer. And then it comes in a little test tube. It's a tiny speck of dust in the test tube, and they put that in a cardboard box and they send it by FedEx. We'll probably optimize the procedure in the future, but at the moment, that's how it's done.
And then you dissolve that, put it in the machine and say, read this the same way we read the human genome.
Exactly, and we designed the whole system so it would use exactly the same procedures that my laboratory colleagues are very familiar with. So instead of starting with DNA from a human genome or another genome you're studying, we started with dry DNA in a test tube, but we designed that we did some extra features in the design so that would then go straight into the standard laboratory procedures for reading it back on another piece of advanced technology, which every self-respecting biolab will have nowadays.
How is this actually going to get applied? Because are we working towards a sort of DNA computer where you won't have a hard disk, but you're going to have a sort of reactor pool on your desktop where you're making DNA molecules? We're
not thinking of working in that direction at the moment. One of the problems is it's still very expensive, and another one is it's not very fast. But the good thing about DNA is it's really, really long-lived. So we've already heard this evening about getting DNA from wolves and things and thinking about that. But if you look at other creatures, we routinely now can sequence DNA from Neanderthals or cave bears, 10,000 years old or more. So it's really stable. So all these things together suggested to us the thing to go for is something that you want to keep a very long time. So DNA will sit there. You don't have to do anything to look after it. If you keep it cool and dry and in the dark, it's good for tens of thousands of years. And the experiment's essentially been done. For example, a woolly mammoth 50,000 years ago crawls out onto the tundra and dies. And then 50,000 years later, we can get DNA back from it. So we're looking at things that you'd want to store a really long time and you don't mind spending quite a lot of money on. So we're thinking, global important archives of, the Doomsday Book, or maybe, US presidential archives, or records about where all the nuclear waste dumps are. Things that you don't mind paying, admittedly, quite a lot. But you really want to know that information is safe somewhere.
I was thinking of whiskey myself. Nick Goldman from the European Bioinformatics Institute, thank you very much. He published that work this week in the journal Nature. Now, you're listening to The Naked Scientist with me, Chris Smith, and also with Ben Valsler. If you'd like to get in touch with any questions or comments, you can email us. It's chris@thenakedscientist.com. You can also tweet @nakedscientists, or you can find us on Facebook.
Now, around this time each year, at least for the past 4 years, an international group of scientists has put together a list of 15 key global conservation issues. Published in the journal Trends in Ecology and Evolution, the project highlights new technologies that could have an impact on the Earth's biodiversity. Richard Hollingham from the Planet Earth podcast has been chatting to the leader of the research team, Cambridge University's William Sutherland.
What we're trying to do is say what are the changes that are likely to happen, and then we can then say what are the consequences likely to be. And many of them are actually good news. New ways of detecting species, for example. It's positive news.
Let's talk about that then. New way of detecting species. This is using DNA. How does it work?
When species live in water, they shed DNA into the water. And with new techniques, we can actually detect very low concentrations of DNA. So instead of having to find a very rare species or an invasive species that you're worried about, instead of having to put on your Wellington boots or your wetsuit and go and find it, you can actually just take a water sample and then see if you can then find the DNA. And it's a much more effective way of detecting various species.
Another technology you highlight, which is, I mean, on the face of it, a wonder technology, 3D printing, being able to put the dimensions of something into a machine and actually to make one. It's like a Star Trek replicator. Positives and negatives again with that.
And it's clearly a very exciting technology, and it means then if you want to buy something, you might be able to make it immediately. Perhaps you can make it in your office, or perhaps if it's something more substantial, you might go down to the high street and have it made for you. But it means that there'll be reduced shipping costs, and you can get things immediately, you can get it in the way you wanted. But it may well have other sort of costs too. It's likely to shift where products are made. It might mean that instead of products being made in places like China, they're being made in your back bedroom. What would the consequences of that be? What are the social and economic consequences and the pollutant problems of generating these products going to be?
Can you answer any of those questions, or is that the point of the exercise, to raise these questions?
Our point is to raise the questions and say we haven't really thought enough about these, and we just want the community to think more about these sorts of issues so that as they start to happen, we have the science in place so we can know what we should be worried about and what actually turns out not to be a particular worry.
Another intriguing item on your list of 15 conservation issues is this one, forest conservation and restoration by micro-unmanned aerial vehicles, essentially using drones developed for the military.
Absolutely, and the military take this very seriously, as we all know. I've heard that the American Air Force have as many unmanned vehicles as they have manned vehicles. And they have lots of advantages. They can go into areas that are unsafe otherwise. And it's now realised they have all sorts of exciting potentials for environmental sampling, such as going and sampling forests. Google has just invested $5 million in this method for looking at illegal hunting. There's a whole range of different techniques, including the planting of forests. And it's likely that you can actually go and plant forests in areas that are very difficult to access. And that technology is developing. So I think we're going to hear a lot more about drones in conservation in the near future.
You've got these 15 issues. The paper that you've published runs to, 7 pages. It's more than a list. You talk about the various issues, but you're mainly raising questions. What is the point of this?
Because there have been various issues in the past, such as biofuels, where there's been the policy initiative has taken place, and we haven't seen that coming up, and we haven't had the science in place, which we should have done. And we want to try to avoid that sort of problem again. We want to identify changes that are likely to happen and encourage the research community to think about those so that when decisions are being made, there's actually a good body of information so we know what are the real concerns and what are the things that actually we might think are concerns but actually turn out not to be important.
Does anyone take any notice?
They seem to do. So we know that people have done research projects as a result of this. We know that the research councils take note of this. We know that a lot of people have taken a lot of interest in this. And the various conservation bodies and other bodies routinely look through this material. So it seems to be having quite a big impact.
William Sutherland from the University of Cambridge. And you can read a full list of all those conservation issues on Planet Earth Online, where you can also find the latest Planet Earth podcast. Just follow the links from thenakedscientist.com/Planet Earth.
And this is The Naked Scientist with Ben Valsler and with Chris Smith. Electronic gadgets and gizmos seem to be constantly getting smaller. Mobile phones and televisions are becoming thinner and lighter. There's a powerful microprocessor in every modern car, and tablet computers are becoming nearly ubiquitous. But where can electronics go from here? They can't carry on getting smaller, but they can become invisible and possibly seamlessly integrate themselves into everyday objects. To achieve this, we'll need new sorts of materials, and Dr. Andrew Flewitt from the Electronic Devices and Materials Group at Cambridge University is working on the materials that may make our electronics disappear in future. A lofty goal. Hello, Andrew.
Hi there.
So how are you going to do this?
Well, the challenge is really to find the right material that can actually work in the vast, diverse range of applications on a diverse range of surfaces. So if we think about trying to make electronics really on everyday objects, we need to be actually able to make it on things like plastic surfaces. So that's a real challenge. We're used to normal sort of crystalline silicon technology, where we can take a silicon wafer and we can then process it in a lab, and we can work with very high temperatures and very expensive processes to make very small objects, to make a very high performance transistor.
Problem is, it's not terribly transparent, is it? It's not terribly easy to make that work on a surface of a piece of packaging, or even, on a contact lens or something.
Precisely. So one approach might be to try and sort of make very small processors that you could mount onto another object, but that's always going to be somewhat intrusive and very unreliable as well. The weak point in most electronic devices is when you actually make a connection from one object to another. That's why sort of laptop display screens tend to break, and you might occasionally see a sort of row or column disappear because the interconnect has failed as you keep opening and closing your laptop computer. So it'd be much better to actually have everything integrated onto one substrate, and that makes it much more robust.
But much more difficult to do.
It is, and so that's why we have to look to new materials. We have to look away from silicon towards materials that we can actually just directly grow onto a diverse range of substrates like plastics.
Is the reason that the microprocessor industry is dominated by silicon purely because we found a material that did what we wanted to do, and we have progressively optimised it and got better at working with it, and we just haven't bothered to look elsewhere in recent years because silicon has made our lives so easy? We've gone down that line.
Silicon has so many advantages. I mean, it's a wonderful, wonderful material, and we've become very good at engineering it. So we know what its physical limits are, and the objective of an engineer is to try and get around sort of the limits that physicists try to put on us. So we've tried to wring absolutely everything out of silicon as a material, but we really are reaching the limits for the purposes of integrating electronics onto everyday objects. The challenge we face there is how you actually make the real device on a surface. What we normally do is to actually start with a gas phase of the elements that we want to make form the device, and then we make those gases condense onto a surface.
And this gives you a thin film over
and this gives us the thin film, exactly. And by changing the composition of the gases we use, we can change the composition of the thin films. So we can go from having semiconductor materials to dielectric materials, which act as insulators, through to conductors, and there you start to get all the building blocks of making a complete electronic device. So we're looking at these new materials that might enable this.
So rather than using silicon, you're saying let's go to the periodic table and pull out some other elements that might have the right characteristics when treated this way to give us all the things that silicon can do and more, but, and this is the key thing, they will work in the context of a transparent surface.
Precisely.
Does such a pipe dream type material exist?
Absolutely.
What is it?
And they're the class of metal oxide materials. So this is where we work with physicists, because physicists are very good at modelling materials and telling us which of the metal oxides are actually going to be of use. So we've been looking particularly at zinc oxide, which is a very nice semiconductor, and we can play around with it by putting other elements in there, things like indium, gallium, to tailor its properties. So that's the point where we start to move from being physicists to engineers. How do we actually engineer the material to have the right properties for the device application?
So once you've got a material that you think will play ball, how do you turn it into something functional? You can coat a surface with it, so you could potentially make something that will stick onto a packet and be invisible, but how do you actually make it do things like be a display or react to an environment to tell me the milk in this container that you're about to put in your tea is off, don't use it?
So to actually achieve that, we're going to have lots of little elements or components to our full system. So at one level you need transistors to actually do logic, to actually be able to take in information, process it and do something with it. But then you're also going to need a power supply, so we need some power to actually drive this thing. We're going to need sensors to actually look at the environment they're in and take that information in. So maybe if we take the food packaging example, something that's actually monitoring, say, the milk in our food packaging and actually understanding what the chemistry going on in the milk is. Has it gone off or not? And then we're going to need a display probably to integrate in it as well, that's actually telling the end user what's going on, or maybe some wireless technology that then communicates with another object that then ultimately tells us what's happening to our milk.
But are we close to being able to do this, or are you literally at the stage where you're finding materials that could be a substitute for silicon but actually making them do something, such as have the contact lens that shows me the map superimposed on the road ahead? Is that a way off?
We're a fair way down the line already. So the first products with these metal oxide materials are actually now starting to come to market. The first application for these is in displays, where there's been a real need to get higher quality displays based on new materials. So most flat panel displays, such as you have in your laptop computer or your mobile phone, use liquid crystal technology. The next generation is starting to emerge with organic light emitting diodes, and that's placing new requirements on the electronics that drives that. And it's turned us from using silicon in that application towards using these metal oxides already there. And some companies in the Far East have announced products that will come out in the next year that actually use these metal oxide materials. We tend to use the phrase IGZO as a buzz phrase for these indium gallium zinc oxide materials. So that will start to appear, and we can piggyback on that now to actually start using this material in other applications as well.
We'll have to get you back to find out once you've got them. Thank you very much. Andrew Flewitt from Cambridge University. Ben?
Well, one ultimate use of new types of displays would be to project your digital information, your emails, your maps, your diary, literally in front of your eyes all the time and overlaid on relevant parts of the real world. Augmented reality technology, that's software and hardware that will overlay this digital information onto real-world images in real time, has been around for a few years, but largely so far it's just been a bit of a novelty. But 2013 looks set to be the year that may change, with a number of companies releasing spectacle-type wearable display screens. And one of those companies is TTP, that's the technology partnership, a Cambridge-based technology development company who are hoping to commercialise this sort of wearable augmented reality technology. We are joined by Luis Diaz-Santana. Luis, what do you bring to TTP that helps you realise this aim?
I am an optics person, and the way we're approaching this is really hard to get the electronics in front of you. And even if you were to put the electronics directly in front of your eye, it would be far too close. So that would work well if you have something at a certain distance. So what we need is to bring some optical approach that can give you this superimposing these images.
So we need to be a bit cleverer than just literally wearing a screen as glasses.
Yeah. So what we are doing is we have developed at TTP a new technology that creates a hidden grating or a hidden structure inside the glasses that it's invisible to you when you're looking through it, but it selectively reflects very, very specific color bands, and we can select red, green, and blue. But you perceive visual color visual image there that looks like real color, while at the same time most of the light coming from the environment around you goes through the glasses and you see the natural scene unchanged. And those special filters reflect light from a microprojector that may be behind your ear, and those filters are now reflecting the light into your eye, forming an image of whatever is in the projector. So you see at the same time the real world and whatever is in the microprojector behind your ear.
So because you're reflecting light from a projector, it means that the light appears to come from much further away, so you don't get all of the focusing issues.
Exactly.
So how do you then hope to use that? What sorts of images do you want to be able to project?
This is a really open question. It's a platform really what we're developing, where you can choose anything that you can put on a projector. You can put them now in front of your eyes. So you can think of if you're driving, you can put whatever you want on the windscreen in front of you, where it's a speed or there's a curve coming, all your GPS information, and you don't have to take the eyes off the road. You can have games. You can go killing zombies on the street. Anything you want. You can go scuba diving and have all your statistics down and in front of you all the time, so you know your decompression routine. You know anything. Pilots can have information of the flight. I don't know, anything you can think of. If it's in front of you, it's in front of you.
So that really is down to the software developers to take your technology and do pretty much whatever they want.
Pretty much, it's a combination of software and technology. For example, if you're going to be putting in a diving mask, you need slightly different optics than you would need for a pair of spectacles that have everything hidden. That there's a form factor that is you don't know that there's something there. Or if it's going to be on the windscreen of a car, again, it's a different optical layout that you may need to achieve that. But the platform we're building would allow you to select any of those applications, and with a combination of the correct optical configuration and hardware and the software, you could achieve these aims.
So it's obviously very versatile, but chemically, how does that selectively reflective surface actually work?
These are called optical coatings, and these are very thin membranes, effectively, that you deposit on top of the material. And by a process of interference, basically, some of the light is selectively reflected, while some of the light is selectively absorbed. You can choose which colors you send into the eye and which colors you let go through. Every normal glasses has something called anti-reflection coatings that you go to the optometrist and they tell you about. You want to use with anti-reflection coating or not. It's the same type of technology that would allow to do this.
And when do you think we're actually going to see people on the street wearing these with extra images projected to their eyes?
Hopefully 2013, as you said.
Thank you ever so much, Luis. That's Luis Diaz-Santana, and he's from Cambridge-based The Technology Partnership.
Now, any type of wearable, portable electronic device is likely to need a way to generate power on the go. But systems embedded into packaging or everyday objects cannot be plugged in, that's obvious, and batteries would be expensive and also impractical. Instead, a PhD student at Cambridge is looking at a new generation of solar materials. They're called thin film solar cells that could be used to produce the required power just where they're needed. And Ben Vousler went to see him.
My name's Robert Waddingham and I'm a second-year PhD student at the University of Cambridge. My PhD is looking at researching low-cost solar cells using metal oxides.
When we're talking about metal oxides, what do you actually mean by that? That covers a huge and diverse array of different compounds.
Yes, it does. I mean, that's one of the beauties of working with metal oxides, is that you have a very, very wide range of materials to work from and engineer specifically to the electronic application that you want. Metal oxides are very interesting materials to work with because they have a wide range of not only visible properties such as transparency and opaqueness, which is suitable for being transparent as well as absorbing sunlight, but they also have a wide range of electronic properties such as insulators, resistors and semiconductors. And it's really how you go about engineering the materials to get the right combination of both the optical and electrical properties that makes this field so interesting.
So what are current solar cells made out of?
So traditionally the solar cells that everyone sees and you would put on your roof and you see are made from silicon. However, a lot of people are doing a lot of research into other materials for solar cells, such as organic materials, plastic type materials, cadmium-based materials, and we're looking at another sort of metal-based solar cell based on copper oxide, which is significantly less toxic and cheaper than cadmium-based cells.
So how do the metal oxide solar cells work? Is it the same physics, just with different materials?
Essentially, yes. So it's the same concept behind all solar cells, that you basically form a semiconductor junction which absorbs sunlight to generate charge carriers, which are then separated by the electronic field in the junction.
And how are you actually going about researching them? How do you build them and then test them?
One of the things we do is we research the individual materials behind the solar cells and work out how we can design them to have optimal properties for our solar cells. And then the other side is obviously building the solar cells and testing them to see whether theoretical predictions about the properties of the materials are realizable and accurate in terms of the cells that you produce.
What was it that drew you to doing a PhD on these sorts of materials?
Well, I initially started working in the clean rooms as part of my fourth-year engineering master's project, and from there I got hooked onto making experiments and making devices out of all these wonderful noisy machines. So from there I went into doing the Photonics Systems Doctoral Training Centre, which gave me funding for 4 years to do a master's and a PhD, and now I research solar cells with a strong systems focus.
So what have we got around us? There's clearly a lot of very high-tech kit. There's lots of steel and chrome and electronics and computers. What actually is this kit and how do you use it?
So this machine that you can hear in the background here is the Hitus sputtering machine produced by PlasmaQuest Limited. It's one of the main machines that I use to produce a lot of my metal oxide materials. It's a sputtering machine which is a physical vapor deposition process. By that I mean we take a metallic target and we use a plasma to physically knock metal ions off the metal target, kind of like throwing a bowling ball down an alley and watching the pins fly out. If those pins were the metal ions, and then those metal ions are dispersed around the chamber and fall on top of a substrate, where we inject some oxygen, which it reacts with, to form a metal oxide film on our surface that we want to coat.
So that must give you enormous control over the thickness of the layers that it lays down and the actual composition.
Yes, the beauty of this system is that we have a large number of electromagnets that allows us to control precisely the properties of the plasma that we use to strip the metal ions from the target, as well as having control over the amount of gas that we put in, the amount of oxygen that we put in, which is all controlled by a computer and allows us to very precisely engineer the exact properties of the films that we make.
So what comes out the other end?
When the process is finished, what we're left with is a very thin film of copper oxide, in this case, on our substrate that we can use to create solar cells, transistors, any basically electronic sort of device that we're interested in making.
And once you've built that thin film of copper oxide, what's the next stage? How do you then take it to test it, to work out if it has the properties you're looking for, and then work out how to apply it in the real world?
So once we have our sort of thin film of copper oxide, we'd be looking at trying to form it into some sort of device, usually by patterning it and adding in some contacts so that we can make an electrical contact to it. Typically we use material like gold. We would use various testing rig type systems, electronic probe stations, to probe the electrical properties and measure things that you might be interested in an electronic material, like its resistance, what its capacitance is like, as well as looking at optical properties like its transparency, its reflectance, how much light it absorbs.
And what are the ideal set of properties that you're looking for in your material?
With the copper oxide, you're both interested in it being an ideal solar absorber as well as an electronic material for the solar cells that we're producing. An excellent optical absorber has an ideal band gap between about 1 electron volt and about 2.2 eV. This is so that it absorbs as much solar radiation as efficiently as possible. On top of that, it needs to have excellent electrical properties so that it can operate as an electronic material. In the case of a solar cell, it needs to be quite conductive, as well as having excellent semiconducting properties so that the charge carriers you generate from the solar radiation can be extracted from the junction efficiently.
So once you have your film and you've measured its properties, you know it's going to do what you want it to do, how do you then start to integrate that with bigger systems?
So one of the main advantages of metal oxides is that you can fabricate them at room temperature. This means that they're ideal to be deposited on plastic-based substrates, which means that we can deposit them on a whole range of different surfaces without any significant issues or intentional heating of the substrate. So this allows us to sort of look at making things for like wearable electronics or largely any surface that we want to deposit on. So things like head-up displays, smart windows, basically any situation where you need to make electronics on an optically transparent type screen is ideal for this sort of cheap fabrication technology.
Robert Waddingham, he's a PhD student at Cambridge University, and he was speaking with Ben Valsler.
And now it is time to join Hannah Critchlow for our Question of the Week, in which she's buzzing about ways to ward off mosquitoes.
This week, we listen in to find out how best to get mosquitoes to buzz off.
Hello, my name is Nikhil Rajagopalan, and I am from Chennai, India. I was at the local store the other day, and I happened to see a small device being sold that claimed to emit sounds at high frequencies and as a result repel mosquitoes. My question is there any peer-reviewed evidence to support their claim?
So, could a high-pitched sound annoy mosquitoes to the extent that they move on?
I'm Dr. James Logan, a medical entomologist from the London School of Hygiene and Tropical Medicine. Now, there are many devices on the market that emit a high-frequency sound and claim to effectively repel mosquitoes. And the devices range from handheld gadgets to even mobile phone apps that you can buy these days. And this high-frequency sound is meant to mimic a natural predator such as a dragonfly. And in nature, female mosquitoes would want to avoid a predator such as this. The other theory is that the sound actually mimics a male mosquito, and if a female has mated already, then she'd want to avoid that male mosquito. So that's the theory behind how these things work. Now, while sound does play a role in mosquito ecology, and mosquitoes certainly do have a sense of hearing, unfortunately there is no scientific evidence that high-frequency devices repel mosquitoes. They're definitely not recommended for use in tropical countries, particularly where diseases like malaria are present. You're much better off using a topically applied repellent, and the best one on the market is one which contains DEET, or diethyl toluamide. A more natural alternative, which can be used in low-risk areas, is a repellent called PMD, or p-menthanediol, which is from the lemon eucalyptus plant. It does smell a bit, and you have to apply it more frequently, but it is a more natural alternative to DEET.
So although it is biologically plausible for a high-pitched sound to annoy a mosquito away, there's no scientific evidence in existence that supports the claim that these devices actually work. High-pitched frequencies do, however, seem to disturb teenagers. The sonic teenager deterrent, nicknamed the Mosquito, sends out 80 decibel bursts of pulsing sounds of at least 16 kilohertz. And to those under about 20 years old, apparently it sounds like a demented insect or a very badly played violin. But for adults, it's hardly detectable. The reason being that over the years, cells in the inner ear die or are damaged, and the ones that go first are the ones that hear these higher frequencies. Apparently these devices are in use by the police forces, and Staffordshire Police confirmed that they stock these sonic devices for deployment in areas hit by teenage trouble. Moving on, James in Cambridge wrote in with this.
Looking around at the neighbourhood cats, it struck me that most of them, and indeed most mammals, have patterned fur with several different colours. This made me wonder why humans tend to have uniform colour hair on their heads, faces and bodies. Why is this? Has there ever been anyone with multicoloured or patterned hair, or is it always a uniform colour?
So, can you get a tabby human? And if not, why not? Send us your thoughts by posting on our Naked Scientists Facebook page. You can tweet at Naked Scientists. You can join in our live debate on our forum, which is at nakedscientists.com/forum, or you can email Chris at thenakedscientists.com.
Hannah Critchlow. That is it for this week, but do be sure to join us next time when we'll be taking a look at the efforts that are going on to save the Tasmanian devil from devil facial tumour disease, this deadly cancer which transmits between them. We'll be asking why it is that the animals don't reject the tumour when it infects them. In the meantime, don't forget you may find out more about The Naked Scientist from our website, nakedscientists.com. You can also send us comments, questions and feedback to chris@thenakedscientist.com. Thank you to our news panellists this week, who were Laura Howes, Mark Peplow and Laurie Winklis, and our guests Andrew Flewitt, Nick Goldman and Luis Diaz-Santana. The Naked Scientist is supported by the EPSRC and the Wellcome Trust and comes to you from Cambridge University. Thank you to Ben Valsler. My name's Chris Smith, and thank you for listening. Goodbye.